Jnanam Paramam Dheyam. Knowledge is supreme.
So, today we discuss NMR spectroscopy in a little more detail than what we have done so far. So far, this is what we have said. In NMR spectroscopy, in any case, is all about spin flipping of nuclei in a magnetic field, right? And we said that not all nuclei are going to respond to magnetic field anyway. What is the essential condition for a nucleus to be NMR active? Non-zero spin angular momentum, right? Non-zero spin angular momentum. So, for proton, the what is the spin quantum number? Yeah, for proton spin quantum number is half, right? Ms, which I have written only as m here, that can be plus half or minus half. What does that mean? What is the length of the spin vector? √3/2, and the orientations can be such so that the z component of the angular momentum, spin angular momentum, can either be plus half or minus half. What is the unit? Plus half or minus half? H cross, h/2 pi, right? So, when we write this, we always write this in terms of h cross. Okay. And as usual, if you find any error on the slide, please feel free to point out. It is human to err. Okay. So, this is what it is. So, what we have said that this spin wave functions for protons are of two types, alpha and beta. Alpha stands for up spin or m equal to half, beta stands for down spin or m equal to minus half. So, we can write this kind of eigenvalue equations where the operator is the Iz operator, wave function is either alpha or beta, and you have the corresponding eigenfunctions h cross by 2 or minus h cross by 2. And then we said that the way you get the Hamiltonian is that you start from here. Hamiltonian, we have said already, is minus gamma B0 Iz, and we are talking about a free proton right now. So, in that case, what is gamma? Gyromagnetic ratio or magnetogyric ratio, both names work. Okay. So, minus gamma B0 Iz operating on alpha, that gives you minus gamma B0 h cross by 2 alpha. So, when the same Hamiltonian operates on beta, you get plus gamma B0 h cross by 2 beta. Okay. So, we had said that that gives us the two energies E alpha and E beta, which are minus and plus respectively half h cross omega beta 0. Okay. And in this energy, B0 is magnetic field and gamma is a property of the nucleus. So, both get multiplied to give you the energies. So, the energies of course depend on not only what kind of nucleus we are talking about, but also on how much of a magnetic field we are using, right. From there we said that in absence of magnetic field, these two spins have the same energy, they are degenerate. In presence of magnetic field, the alpha spin gets stabilized and the beta spin gets destabilized, and the energy difference we had said is your gamma h cross B0 we had calculated, and from there we equated that to h nu L, when nu L is essentially Larmor frequency, the frequency of the light that is absorbed on one hand, and in the classical model frequency of precession of this angular momentum vector around the z axis. So, this is called Larmor frequency commonly, L stands for Larmor. That is equal to gamma B0 by 2 pi. Please remember this, we are going to use this quantity a little later. Alright. So, and we had discussed that you can work out what will be this precessional frequency or Larmor frequency for what kind of magnetic field. Okay. And then we said that, but then we are not really interested only in bare proton. The reason why NMR is useful for chemists is that it can report the chemical environment, because in any compound the proton is actually engulfed in this charge cloud, electron cloud, right, and that acts as a shielding medium. So, it allows only an effective magnetic field to be felt by the nucleus. So, from there we said that the field on the nucleus is B effective, that is B0 multiplied by 1 minus sigma, where sigma is the shielding constant. Hence, we had to modify the expression for Larmor frequency for proton in a compound, that became gamma B effective this time divided by 2 pi, therefore, 1 minus sigma multiplied by gamma B0 by 2 pi. And we said qualitatively that if you have nuclei in different environments, you expect resonances at different places. So, you expect that a low resolution NMR spectrum of ethanol will be something like this. Then we performed a discussion on the delta scale, where we said that since we have already understood that frequency actually depends not only on the nucleus, but also on the applied magnetic field, we do not want to have different values if we use different instruments. We want the same spectrum for the same compound irrespective of which instrument we use. So, it is better to shift to a relative scale, and the relative scale is nu minus nu 0 by nu 0 in 10 to the power 6. That turns out to be something called delta, which is completely independent of the field. This is where we stopped. And we said that generally you use tetramethylsilane, which is a good standard for several reasons. We had also said that it is not necessary that it is always shielding. Sometimes you can have deshielding, and to demonstrate that, we have taken this example of aromatic compounds, where in different positions protons can get either shielded or deshielded. Okay. And then we had ended the discussion by showing you an actual spectrum of ethanol, where some of our expectations are fulfilled. You do have 3 groups of lines, no problem with that. If you take areas under each of these groups of lines, that gives you a measure of abundance, no problem with that. But the question is, why is it that we have groups of lines instead of a single line? And we had said once again qualitatively that what happens is, say CH2 proton also has the CH3 proton nearby. So, these are like small magnets which are not only in this big magnetic field B0, but also they feel the presence of each other, and this feeling the presence of each other of the small magnets goes by the name of coupling. So, what is the meaning of coupling? I am the big magnetic field. So, by and large you look at me, but then you can also talk to each other, right. So, we talk to each other, that is coupling, and we will come back to this talking to each other. It is actually it helps us understand something, but if you talk to yourself, then there is a problem, right. Self coupling is not good. Karthik calling Karthik, right. So, today let us try to build this quantum mechanical treatment of a 2-spin system. We will call them A and X. A and X means that the sigma values are very different, shielding constants are very different from each other. That is the meaning of A and X. So, in an alphabet, A and X are separated by many letters, right. So, that is why it is called A and X. There is another system that we are going to discuss later on, that is called the AB system. A and B are next to each other. Okay. We will also talk about A2 system, talking to oneself. Okay. But let us start with the simplest of all these, that is the AX system, where there is no spin coupling. Okay. Now, if we take an unperturbed system, I hope it is not very difficult to understand that this is going to be the sequence of energies. We said that in presence of magnetic field, alpha has lower energy, beta has lower energy. So, what is the most favorable situation? Both A and X have alpha spin, yeah, just because it is down I was pointing downwards, it should be like this. Both A and X have alpha spins. What is the most unfavorable, most highly energetic situation, where both A and B have, A and X have beta spins, okay, and there will be 2 intermediate situations, A has alpha spin, B has beta spin, and the reverse, not B, X. This is a problem. Whenever you say A, automatically you think B. In this case, it is not B, it is X, right. So, most favorable situation, both A and X have alpha spin. Most unfavorable high energetic situation is both A and X have beta spin. Intermediate is A having alpha, B having beta, X having beta, or A having beta, X having alpha spin. Okay. So, even though I faltered, finally we got it right. This is the situation. Now, out of these two, alpha A beta x and beta A alpha x. We have drawn alpha A beta x at a lower energy than beta A alpha x. What does that mean? If alpha A beta x has a lower energy than beta A alpha x, what does it mean? Yes, sigma of A is greater than or lesser than sigma of x. Sigma of A is lesser than sigma of x. What that would mean is that the effective magnetic field for A is greater than the effective magnetic field for x. Is that right? Does that make sense? If the effective magnetic field is greater for A compared to that of x, then out of alpha A beta x and beta A alpha A beta x should be an energetically lower kind of situation. Do we agree with that? Yes. What was that? Switching? Let us not talk about switching, let us just talk about alpha and beta. Magnetic field for A is higher. Okay. Oh, what he's saying is that then the energy gap for A should be greater than energy gap of x. Do we agree with that? Yes. So, they are going to resonate at different frequencies, and which will resonate at higher frequency, A or x? A. Yes. So, you are right so far, but then I think in the next step you are trying to justify what you said by saying what you said. So, that is like a little bit of circular logic. Up till now whatever you are saying is right, and you have made an important point that A and x are going to have different resonance frequencies. Are we clear? For the same B0 value, A and x will resonate in different places. That is what we had said for your ethyl alcohol case anyway. Fine? Great. Now, let us move on a little bit. To start with, let us imagine that there is no spin-spin coupling. Nobody in the class is talking to each other, everybody is under my great influence, okay? No coupling. Then what are the energetics, what kind of spectrum do you expect? This is the Hamiltonian in that case. Hamiltonian for the first, for A, I have to write minus gamma B0, 1 minus sigma A multiplied by Iz of A. I have to bring in A and x because now we have two nuclei, right? If I just write Iz, that is not enough. One Iz will be in terms of A, another Iz will be in terms of your capital X. So, this is my Hamiltonian, gamma B0 is common, and then I have 1 minus sigma Iza plus 1 minus sigma A Iza plus 1 minus sigma x Izx. Here we have accounted for the fact that sigma A and sigma x are different from each other, and as you have said correctly, sigma A is greater than or lesser than sigma x? Yes, lesser than sigma x. Good. So, this is the Hamiltonian, and you might notice that I have written this Hamiltonian not just as H, but as 0th order Hamiltonian. There is a 0 as a 0 on the top inside bracket, that means 0th order Hamiltonian, uncorrected Hamiltonian, which means that I am still assuming that the nuclei experience the external magnetic field and do not couple with each other. Coupling will come in later on as a perturbation term. So, remind me once again, how many of you have not studied perturbation theory? Do not feel shy to raise your hand, the other guy is not here. 1, 2, 3, 4, fine. So, we will as we go along, we are going to build a working knowledge of perturbation theory to the maximum, to the extent that we need. So far, are we all okay? I am saying there is absolutely no coupling. So, the Hamiltonian, the uncorrected 0th order Hamiltonian is this minus gamma B0 into 1 minus sigma A Iza plus 1 minus sigma x Izx. So far so good. Now, what do we have to do? We have to take the wave functions one by one and make this Hamiltonian operate on it. Let us do that. what have I written? IZA, right? Sigma x, I was going to write sigma b once again, IZ x. Great. This is my Hamiltonian, and let us say that operates on the lowest energy wave function alpha a alpha x. What do I get? Minus gamma b0 is common, and here I have 1 minus sigma a, IZA operating on alpha a alpha x. What do I get? Alpha x comes out, right? IZA operates only on alpha a, not on alpha x. So, alpha x remains there. What happens when IZA operates on alpha a? What do I get? Yes, h cross by 2 multiplied by the same alpha a. So, finally I get h cross by 2 alpha a. Well, I can take alpha a outside the bracket also. I mean, I will take alpha a alpha x out of the bracket. Here I have h cross by 2. What about this? 1 minus sigma x, exactly same. IZX operates on alpha x and not alpha a, but again you get h cross by 2. H cross by 2 and alpha a remains. So, I can take this h cross by 2 out and write something like this. Minus gamma b0 h cross by 2 into 1 minus sigma a plus 1 minus sigma x alpha a alpha x. What is the energy in that case? Is this an eigenvalue equation? Yeah. So, whatever I have here, this is the energy of the alpha a alpha x state. So, this is what it is. This is the unperturbed energy of the first level, the lowest energy level. E10 is equal to minus gamma b0 h cross. Then I have written 1 minus sigma a plus sigma x by 2. Does this follow from that or not? Actually, I have just taken 2 inside, that is all. Okay? So, this is the form in which I write it. Can you do the same treatment for alpha a beta x and tell me what you get? Alpha a beta x, that is the next one. Let the 0th order Hamiltonian operate on alpha a beta x. So, does 1 remain or does 1 go? There is no 1 left, right? So, you have sigma a minus sigma x or sigma x minus sigma a, right? And then is there a minus sign outside? So, this is my answer. Is that your answer? Yeah. So, I insist on writing the minus sign outside because first is it is actually stabilization, right? Total negative energy. You are doing sigma x minus sigma a, as you have told me sigma a is less than sigma x. So, it is a negative quantity. I want to make that explicit. Okay. What will happen if you try to do the same thing for beta a alpha x? Same thing without a minus sign. So, now you have destabilization little bit, positive energy. And what happens if you make the Hamiltonian operate on beta a beta x? Same thing as what you did here, only minus will come in both the cases, right. So, this is what you get. Okay. Nice, very nice expressions, 2 groups, right, 2 kinds of expressions, and then you have minus and plus. So, this is the order of energies E10, E20, E30, E40 in increasing order of energy, and this is what you have. These are our expressions. All right. Now, suppose I am talking about this transition alpha a alpha x to alpha a beta x. Which spin gets flipped? Alpha a alpha x to alpha a beta x. X, spin of x gets flipped and spin of alpha does not get flipped. Sorry, spin of a does not get flipped. Is that right? So, what energy expression should I get without doing the math? I have alpha a alpha x, I am going to alpha a beta x. So, a remains in alpha spin state, spin of x flips from alpha to beta. So, what kind of energy should I get? Yeah, something like that, right. So, I should get a resonance that is typical of x, right, and that is building upon what Yuval had said. So, this let us do this, no change in spin for A, and for this transition there is a spin flip for X. Can you subtract E10 from E20 and tell me what you get? Is that what you get? Gamma B0 H cross multiplied by 1 minus sigma X. Do we agree that this is the energy gap for X? Alright. So, this transition is essentially associated with characteristic resonance frequency of X. Alright. Is there any other transition which has no change in spin of A and spin flip for X? What about beta A alpha X to beta A beta X? There also you have the same thing, isn't it? Okay, I forgot to write that H nu X. So, beta A alpha X to beta A beta X. There also we get no change in spin for A and we get a spin flip for X. And remember something, are all these levels populated or not? All these levels are definitely populated. Remember, we have discussed that these energy gaps we are talking about these are radio frequencies, right. So, they are less than microwave. Even for microwave, for rotational levels, we had seen that higher levels are populated, sometimes to a considerable extent, right. So, here since the energy gap is small, then the higher levels will definitely be populated. So, this transition that we are talking about, this is horrible, so I have to stay there. Beta A to alpha X to beta A to beta X definitely is going to show up, and that again is a characteristic transition of H nu X. And I hope it does not take much for you to subtract E30 from E40 and get the same result. Expressions are the same, right, only plus minus these values are different. Earlier you had minus in both, now you do not. So, that is the same thing, E40 minus E30, you get characteristic resonance of capital X. Okay. So, we have two, let me try to draw the spectrum now. This is, let us say, nu X. Here I expect to get a line, okay, and this line is a result of not one but two different transitions. Are we clear? Now, what about the other scenario where A undergoes a spin flip and X does not? Is there any such transition possible here? Yeah. If I start from here, alpha A alpha X to, where should I go? Beta A alpha X, this transition. Can we work out the energy gap? Hey, अपने नाम में sign करो और pass it on. Nosy Parker. Yes. Do you have an answer? E30 minus E10, how much is that? Well, you can guess the answer, but I want you to work it out and convince yourself that the answer that you have guessed is the correct answer. Remember what is happening here? Yeah, same thing as what we have got earlier, instead of sigma X you will get sigma A. So, that is going to be a characteristic transition for A, alright, and this transition is also the same, right, alpha A beta X to beta A beta X. Again X remains in beta spin, A spin flips from alpha to beta, okay. So, once again we expect a line at the characteristic resonance for A. Are we clear? Which one is greater, nu A or nu X? I am asking about nu. In fact, we have answered this question a little while ago. Okay. Between A and X, which nucleus experiences a greater magnetic field? A. So, for greater magnetic field splitting will be more. If splitting is more, nu is going to be larger. Okay, great. And that is the convention, that is how you write A and X. Alright, so this is what we have got for the unperturbed system. But before we leave this story, can we have another kind of transition? A goes from alpha to beta, X also goes from alpha to beta, or something like that. Can both spins flip? So, can I have this kind of a transition, alpha A alpha X to beta A beta X? Can I have this kind of a transition, alpha A beta X to beta A alpha X? Of course, when I ask like that, the answer is going to be no, and we have discussed it. You are right. It cannot happen because our photons are not like Rajnikant's bullets. Remember, one bullet can only kill one villain. One photon can only bring about one transition. So, because of one photon rule, you cannot have both spins flipping in the same transition. Okay. So, you will not see any other line in the NMR spectrum for an AX system if A and X do not talk to each other. That is the conclusion of our story for the unperturbed AX system.